please subscribe to support the channel. The question of how long it would take to reach the Andromeda Galaxy sparks both scientific curiosity and deep human wonder. Andromeda, that faint blur visible in the night sky, isn't just another point of light, it's a massive spiral galaxy, home to 1 trillion stars, lying far beyond the borders of our Milky Way. Asking how long it would take to reach it isn't merely about distance, it's about possibility, about measuring the limits of our technology and imagination. This question fascinates astronomers because it challenges our understanding of scale and motion in the universe, while inspiring dreamers to imagine journeys across cosmic oceans far larger than anything humanity has ever faced. In asking it, we're not just wondering how far away Andromeda is, we're asking how far we, as a species, might someday go. To understand what it really means to ask how long it would take to reach the Andromeda Galaxy, we first need to understand what Andromeda actually is and how it fits into the vast structure of the cosmos. The Andromeda Galaxy, also known as Messier 31 or M31, is a sprawling spiral galaxy much like our own Milky Way, but even larger, stretching more than 220,000 light-years across. It contains roughly 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. When we look at Andromeda through a telescope, we're gazing at a colossal collection of suns, worlds, gas clouds, and star clusters, all bound together by gravity in an elegant rotating spiral that has existed for billions of years. In cosmic terms, Andromeda is our nearest large galactic neighbor. Though it lies about 2.5 million light-years away, that makes it close by the standards of the universe. Between galaxies, space stretches over truly mind-bending distances. Most galaxies are tens or even hundreds of millions of light-years apart. The Milky Way and Andromeda are part of a small community of galaxies called the Local Group, a gravitationally bound cluster that also includes the Triangulum Galaxy, M33, and dozens of much smaller dwarf galaxies. Within this neighborhood, Andromeda and the Milky Way dominate like twin giants, orbiting one another in a slow cosmic dance. What makes Andromeda particularly fascinating is that it's not drifting away from us like most galaxies in the universe. Because of the overall expansion of space, nearly every other galaxy is racing away from the Milky Way, with their light stretched and redshifted as space itself expands. But Andromeda is different. It's actually moving toward us, pulled by mutual gravitational attraction at a speed of about 110 kilometers per second. This means that far in the future, around 4 billion years from now, the two galaxies will merge to form an enormous elliptical galaxy, sometimes nicknamed Milkomeda. So in a very real sense, Andromeda is both our neighbor and our eventual destination, though on a timescale that dwarfs human history. When we talk about its position in the night sky, Andromeda lies in the constellation of the same name, visible to the naked eye under dark conditions as a faint misty smudge just above the horizon in the northern hemisphere's autumn skies. That smudge, however, is not a star or a cloud. It's the light from billions of stars so distant that their glow blends into one soft haze. Every photon from Andromeda that reaches your eyes tonight began its journey long before humans even existed, traveling across the void for millions of years before ending its voyage on our tiny planet. This perspective helps us grasp the true scale of the question we're asking. The Andromeda Galaxy isn't just far, it's unimaginably far. Even the fastest signals we can send, such as beams of light or radio waves, take millions of years to cross the gap. That distance defines the challenge. To reach Andromeda, we would need to traverse not just the emptiness between stars, but the vast gulf between galaxies themselves. And as we'll soon see, that number, the actual distance in measurable terms, will make the scale of this cosmic journey even more staggering. When we say that the Andromeda Galaxy is about 2.5 million light-years away, it's easy for the mind to gloss over just how enormous that distance truly is. A light-year sounds poetic, almost abstract, but what it represents is one of the most staggering measures in all of science. The Andromeda Galaxy isn't just far, it's so distant that the light we see from it tonight began its journey when early human ancestors were still learning to use simple tools. Every shimmer of light from that galaxy has been traveling through the silent void of space for 2.5 million years before finally arriving at Earth. To put that in a form we can attempt to grasp, 1 light year equals roughly 9.46 trillion kilometers, or about 5.88 trillion miles. Multiply that by 2.5 million, and you get a distance of approximately 23.65 quintillion miles. That's 23,650 billion miles. Written out fully, it becomes almost unreadable, a string of numbers that stretches the limits of comprehension. Even in kilometers, the number is mind-bending, about 24 quintillion kilometers. If you were to drive toward Andromeda in a car at highway speed, it would take you roughly 4.5 trillion years, far exceeding the current age of the universe.
For context, light, the fastest thing in existence, travels at about 300,000 kilometers per second, and it still needs 2.5 million years to cross that gap. The distances between planets within our solar system suddenly feel microscopic in comparison. The Earth is just 8 light minutes from the Sun. The farthest planet, Neptune, is about 4 light hours away. Even the outer edge of our solar system, where Voyager 1 now drifts, is only around 1 light day away. And yet Andromeda sits 2.5 million light-years beyond that frontier. Another way to think of it is this: if you shrank our entire solar system down to the size of a coin, the Andromeda Galaxy would still be thousands of kilometers away at that same scale. That's how immense the gulf of intergalactic space is. It's not a void we can imagine crossing in human terms. It's a realm where ordinary measures like speed and distance start to lose meaning. This vastness isn't just a matter of numbers. It's a reflection of the universe's architecture. Between the Milky Way and Andromeda lies nothing but sparse intergalactic gas and dark matter, an emptiness so profound that entire galaxies could pass through each other with barely a single star colliding. And in that emptiness, light itself, the universe's fastest messenger, creeps along for millions of years, linking 2 great spiral galaxies in an invisible bridge of ancient photons. When you look up and spot Andromeda, you're literally looking into the past, seeing the galaxy as it was when early humans hadn't yet walked fully upright. Every single atom of light that reaches you carries a story that began before recorded history, crossing a distance so vast that words struggle to describe it. So when we ask how long it would take to reach Andromeda, we're really asking how long it would take to traverse a gulf that light itself requires millions of years to cross. It is a distance that humbles even the grandest ambitions of science and technology. And as we'll soon see, understanding what a light year truly means will help make sense of just how extraordinary this challenge really is. A light year is one of those scientific terms that almost everyone has heard of, yet few people stop to think about what it really means. It sounds like a measurement of time, after all. It includes the word year. But in truth, a light year is a measure of distance. And not just any distance, but one so immense that ordinary units like kilometers or miles become practically useless. To truly grasp how far away something like the Andromeda Galaxy is, we must first understand the nature of this unit, the light year, and the staggering speed it represents. Light is the fastest thing in the universe. According to Einstein's theory of relativity, nothing with mass can move faster than light in a vacuum. Its speed is constant, unwavering, and fundamental to the structure of reality itself, about 299,792 kilometers per second, or roughly 186,282 miles per second. To put that into perspective, in the time it takes you to blink your eyes, light has already traveled around the Earth's equator more than 7 times. In a single second, it could travel from Earth to the Moon and back, more than once. It's so fast that even our most powerful rockets look motionless in comparison. So when astronomers talk about a light year, they mean the distance that light can travel at that incredible speed in 1 year. Let's break that down. There are about 31.56 million seconds in a year. Multiply that by light speed, roughly 300,000 kilometers per second, and you get a number so large it almost loses meaning. 9.46 trillion kilometers, or about 5.88 trillion miles. That's just one light year, one single year of travel for light, the universe's fastest traveler. Now imagine extending that across millions of years. The Andromeda Galaxy, for instance, is about 2.5 million light years away, meaning that the light you see from it tonight left there roughly 2.5 million years ago, long before modern humans evolved. Every single star you can see in Andromeda's glowing spiral arms is an ancient beacon, sending its light toward us before our species even existed. In that sense, when you look at Andromeda, you're not seeing it as it is today, but as it was in the deep past. The galaxy itself could look very different right now, but we won't know for another 2.5 million years because the information, the light, is still on its way to us. This concept of a light year doesn't just tell us about distance, it also connects directly to time. In the universe, distance and time are inseparable. Every time we look deeper into space, we're also looking further back in time. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. So if something were to happen there right now, we wouldn't know about it until over 4 years later. The light year thus becomes a kind of cosmic time capsule, encoding the delay between when an event occurs and when we finally perceive it. But what makes the light year so important in this discussion is how it exposes the limits of our technology. The fastest spacecraft ever built by humans, such as NASA's Parker Solar Probe, travels at about 700,000 kilometers per hour, less than 0.07% the speed of light. That means that in 1 year, Parker Solar Probe covers less than 1/10,000th of a light year. Even if it could keep that speed constantly, it would take tens of thousands of years just to reach the nearest star system, and unimaginable stretches of time to reach another galaxy. The light year gives astronomers a convenient shorthand for describing such mind-boggling distances without drowning in zeros. Instead of saying 9 trillion kilometers, it's easier to say 1 light year. But make no mistake, that single word represents a vastness that defies comprehension. When scientists measure galaxies in millions or even billions of light years, they're describing spans of space and time so immense that even light, moving at the ultimate speed limit of the universe, requires eons to cross them. And it's also important to remember that light doesn't slow down or tire out. The photons that left Andromeda millions of years ago have been sailing through the vacuum of space, unimpeded, unaffected by friction or resistance. Space is so empty that a single beam of light can travel indefinitely until absorbed by dust, gas, or a planet that happens to lie in its path. This is why we can still see the glow of Andromeda after millions of years. Those ancient photons have finally reached us, bearing witness to the galaxy's distant past.
There's something profoundly humbling about this. Every image we have of distant galaxies, every beautiful photo from the Hubble or James Webb Space Telescopes is not a snapshot of the present, but a glimpse into cosmic history. Light years don't just measure space, they measure time itself. They remind us that when we look into the sky, we're peering backward into the story of the universe, seeing it unfold across billions of years. Understanding what a light year means gives us the foundation we need to appreciate the true scale of the Andromeda question. When we say it's 2.5 million light years away, we're saying that even light, racing at 300,000 kilometers per second, takes millions of years to reach it. The sheer enormity of that distance dwarfs every human endeavor, every ship ever built, every dream of exploration we've yet imagined. But this is also what makes the idea so inspiring, because knowing the scale of what lies beyond only fuels our desire to keep pushing further into the unknown. As we continue, we'll see how this immense distance compares with the size of our own galaxy and the space between nearby stars, and how, when viewed in that context, the journey to Andromeda becomes even more breathtaking to imagine.
When we begin to compare the distance to the Andromeda Galaxy with the distances within our own Milky Way, the immensity of intergalactic space becomes almost surreal. The Milky Way itself is enormous, a majestic spiral disk of stars, gas, and dark matter stretching roughly 100,000 to 120,000 light-years across. To put that in human terms, even if you could travel at the speed of light, it would take you about 100,000 years to go from one side of our galaxy to the other. And yet, when you place that number beside the 2.5 million light-years separating us from Andromeda, the Milky Way suddenly feels almost small, like a single island floating in a vast cosmic ocean. To give a sense of scale, imagine the Milky Way as a dinner plate about 30 centimeters wide. At that scale, the Andromeda Galaxy would be another plate of roughly similar size, but it would be sitting about 7 or 8 meters away. The space between those two plates is not filled with stars, planets, or dust in any noticeable concentration. It's nearly pure emptiness, a silent gulf where the nearest stars to one another might be separated by tens of trillions of kilometers. When we say intergalactic space, we're describing one of the most desolate stretches of the known universe. Now, within our own Milky Way, the distances between stars are already vast beyond ordinary comprehension. The nearest star system to Earth, Alpha Centauri, lies about 4.24 light-years away. That means even light, traveling at nearly 300,000 kilometers per second, takes over 4 years to make that journey. The Voyager 1 spacecraft, the farthest human-made object from Earth, has been traveling outward since 1977 and has just barely reached interstellar space, a little over 23 billion kilometers from home, or about 0.002 light-years. At its current speed, it would take Voyager more than 75,000 years to reach Alpha Centauri, and that's just the nearest star, not even another galaxy. Now, extend that comparison outward. The Milky Way is composed of hundreds of billions of stars, spread across that 100,000 light-year span. If you were to imagine jumping from one star to the next, traveling at the fastest possible human speed, say the speed of the Parker Solar Probe at around 700,000 kilometers per hour, it would take you over 6,000 years just to reach the nearest star. To cross the entire galaxy would take tens of billions of years at that same speed. And yet, to reach Andromeda, you'd have to travel a distance 25 times greater than the entire width of the Milky Way itself. Even our closest galactic neighbors beyond the Milky Way, such as the Large and Small Magellanic Clouds, which are small satellite galaxies orbiting us, are only about 160,000 to 200,000 light-years away. That's still relatively close compared to Andromeda's 2.5 million light-year gulf. These dwarf galaxies are like small islands hovering near the edges of our galactic continent, while Andromeda is an entirely separate continent across an almost unimaginably vast cosmic sea. It's helpful to think of scale in another way. If our entire solar system were shrunk down to the size of a grain of sand, then the Milky Way would be about the size of North America, and Andromeda would be sitting all the way across the Pacific Ocean. Between them would be nothing but empty cosmic water, incredibly sparse hydrogen gas, and invisible dark matter. That's how lonely the space between galaxies truly is. What's more astonishing is that both the Milky Way and Andromeda are moving toward each other at tremendous speed, about 110 kilometers per second. Even at that velocity, it will still take around 4 billion years for the two galaxies to collide. That's a measure of just how vast the space between them is. Even moving hundreds of kilometers per second, the journey takes billions of years. It's a humbling reminder that our human sense of distance and time simply doesn't apply on galactic scales. When astronomers map the local group, the cluster of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies, what emerges is an image of islands floating in an almost perfect void. Most of space is not filled with stars, planets, or dust, but with empty darkness. The density of matter in intergalactic space is so low that on average you might find just one atom in every cubic meter. If you were traveling between galaxies, you'd be moving through an emptiness so complete that you could go years without encountering even a single particle of dust. Comparing these distances reminds us that our galaxy, vast as it is just a tiny component of a much grander cosmic tapestry.
The distances between galaxies dwarf even the most extreme scales within the Milky Way. Traveling between stars is already a monumental challenge. Traveling between galaxies is an entirely different level of impossibility, at least with the technology we have today. And yet, understanding this comparison is essential to appreciating the true wonder of the question we're exploring. It tells us that the Andromeda Galaxy isn't just far away. It's beyond the horizon of everything humanity has ever touched or built. It sits across a gulf of space so large that even light, the universe's fastest messenger, takes millions of years to bridge it. This realization doesn't make the dream of reaching Andromeda less fascinating, it makes it even more profound. Because when we talk about traveling to another galaxy, we're no longer talking about journeys within a star system or even a galaxy. We're talking about traversing the deepest and emptiest regions of the universe itself. And before we can imagine how long such a journey might take, we must first ask, what would it even mean to travel across such a void with the technology we have today?
Now that we understand the sheer scale of the distance to the Andromeda Galaxy, a staggering 2.5 million light-years, the next natural question arises, if we actually tried to travel there, how long would it take? It's a question that sits at the intersection of science and imagination, one that forces us to confront both the power and the limitations of human achievement. Because while the numbers may seem abstract, they become soberingly concrete when we begin to calculate them in terms of real travel times. Humanity has long dreamed of journeying beyond the familiar boundaries of our solar system. The idea of traveling to another galaxy captures that dream in its most extreme form. Yet, before we can even think about reaching Andromeda, we need to translate cosmic scales into human terms. It's not enough to say millions of light years. We have to ask, at the speeds we can actually achieve, how long would it take? The answer, as you might expect, is almost beyond belief. Let's start with what we have. The fastest spacecraft humans have ever built are technological marvels by any ordinary standard, capable of crossing millions of kilometers through the void of space. But in the context of intergalactic distances, their speeds are like the crawl of an insect compared to the speed of light. Even within our own solar system, travel times are measured in years. For instance, it took the Voyager 2 probe 12 years just to reach Neptune, the outermost planet, traveling at tens of thousands of kilometers per hour. And that's within a region of space that's less than a single light day across. When we expand our ambitions beyond the solar system to the nearest stars and eventually to other galaxies, those speeds suddenly look painfully slow. At Voyager's current velocity, it would take about 75,000 years to reach Proxima Centauri, the nearest star system, only 4.24 light-years away. That's nearly 100 times longer than all of recorded human history. But the distance to Andromeda isn't just a few light-years, it's 2.5 million light-years. That's about 600,000 times farther than Proxima Centauri. Even with our fastest spacecraft, the journey would take on the order of tens of trillions of years, vastly longer than the current age of the universe itself, which is about 13.8 billion years. To imagine this in a more personal way, picture launching a spacecraft today, one built with the most advanced propulsion technology humanity has ever achieved. It leaves Earth, escapes the solar system, and begins the long voyage toward Andromeda. Long before it has made even the tiniest fraction of progress, perhaps only after a few dozen light years, our sun will have long since burned out. The Earth will have ceased to exist as a habitable world, and humanity as we know it will likely have evolved into something entirely different if it exists at all. And still, that spacecraft will be nowhere near Andromeda. This is why the concept of travel time becomes both a scientific and a philosophical question. It forces us to grapple with the nature of cosmic distances and the limits of our technology. When astronomers or physicists talk about intergalactic travel, they're not just discussing propulsion systems, they're touching on the boundaries of physics itself, on the limits of what's possible for beings constrained by time, matter, and energy.
Even if we imagine a scenario where our spacecraft could travel faster than any probe we've ever launched, say at 1% the speed of light, that's still about 3,000 kilometers per second, thousands of times faster than Voyager or Parker Solar Probe. Yet at that incredible velocity, it would still take roughly 250 million years to reach Andromeda. Think about that. Even moving at a speed that would carry you from Earth to the Moon in a single second, the journey across intergalactic space would last hundreds of millions of years. The scale of that distance transforms time into something almost meaningless on a human level. So when we ask the question, how long would it take to reach the Andromeda Galaxy? We are really asking, what does distance even mean when the numbers become this large? Because with today's technology, the answer is brutally simple. It would take far, far longer than the universe has even existed. The journey is so long that no ship, no civilization, no species, at least as we understand them, could survive to see the end of it. But this question also has another layer to it. It doesn't just reveal how far away Andromeda is, it highlights how young we are as a technological species. Human spaceflight, as incredible as it seems, is still in its infancy. We've only been sending machines beyond our planet for a few decades. The fact that we can even calculate what such a journey would entail is a testament to how far our understanding has already come. Still, the cold math of travel time remains inescapable. To cross the gulf between galaxies with current propulsion systems would take longer than the lifespan of stars, longer than galaxies have existed in their current forms. It's not simply impractical, it's impossible, at least for now. But this realization doesn't extinguish our curiosity. It only pushes us to imagine what kinds of breakthroughs might one day make the impossible possible.
And that brings us naturally to the next step in our exploration. If we want to understand just how unattainable Andromeda is with our current capabilities, we need to look closely at the fastest spacecraft humanity has ever built, the true limits of our propulsion technology, and how even our greatest engineering achievements barely make a dent against the backdrop of intergalactic space. When we begin to discuss the idea of traveling to the Andromeda Galaxy, it's natural to wonder what humanity's fastest spacecraft are actually capable of. The truth is both inspiring and humbling. While our spacecraft represent some of the most remarkable technological achievements in history, their speeds are minuscule compared to what would be required for intergalactic travel. Even so, examining these spacecraft, from the legendary Voyager probes to the cutting-edge Parker Solar Probe, gives us a clear picture of the progress we've made and the vast gulf that still remains between human engineering and the cosmic scale of the universe. Let's start with two of the most iconic spacecraft ever launched, Voyager 1 and Voyager 2. These twin probes were launched by NASA in 1977, originally designed to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune, before continuing their journey out of the solar system. Over 4 decades later, both are still traveling through space, now in the region known as interstellar space, where the influence of the sun's solar wind gives way to the faint plasma between the stars. Voyager 1, the faster of the two, currently travels at a speed of about 61,000 kilometers per hour, roughly 38,000 miles per hour. That's fast enough to circle the Earth in less than 40 minutes. But even at that blistering speed, it would take Voyager 1 about 75,000 years just to reach the nearest star system, Alpha Centauri, located 4.24 light-years away. To reach Andromeda, 2.5 million light-years away, Voyager 1 would need more than 100 trillion years. For comparison, the entire age of the universe is about 13.8 billion years. That means Voyager would have to travel almost 10,000 times longer than the universe has even existed to make it to Andromeda. The numbers are so extreme that they border on absurd. And yet, Voyager 1 remains one of humanity's greatest achievements, a tiny ambassador of Earth drifting through the infinite,
carrying a golden record with sounds and images from our planet, a message to any civilization that might one day encounter it. Then there's the New Horizons spacecraft, launched in 2006 to study Pluto and the outer regions of the solar system. After its historic flyby of Pluto in 2015, it continued into Kuiper Belt, moving at around 58,000 kilometers per hour, about 36,000 miles per hour. Like Voyager, it's headed into interstellar space, but even at that speed, it would also take tens of thousands of years to reach just the nearest star. The real record holder, however, is NASA's Parker Solar Probe, launched in 2018. Designed to study the Sun up close, it has achieved speeds that dwarf those of any previous spacecraft. During its closest approaches, it travels at about 700,000 kilometers per hour, approximately 430,000 miles per hour. That's fast enough to go from New York to Tokyo in less than a minute. In fact, relative to the Sun, it's the fastest object humanity has ever created. It's moving at roughly 0.064% the speed of light, still tiny in relativistic terms, but astonishing by human standards. To understand what that means, let's put it into context. Light travels at about 1,080,000,000 kilometers per hour, so Parker Solar Probe is moving about 1,500 times slower than light. If it could somehow maintain its maximum speed in a straight line toward Andromeda, the journey would still take roughly 40 billion years. That's almost 3 times the current age of the universe. Even the fastest spacecraft humanity has ever built wouldn't make a noticeable dent in the distance between galaxies. And yet, these numbers shouldn't discourage us. They should inspire awe. Think about what it means for a human-built object to move at hundreds of thousands of kilometers per hour through the emptiness of space. Parker Solar Probe endures temperatures of over 1,000 degrees Celsius near the Sun, collects unprecedented data on solar wind, and survives conditions no other spacecraft has ever faced. Voyager 1, despite being launched nearly half a century ago, continues to send faint signals home from more than 24 billion kilometers away. That's a testament to human ingenuity and persistence. When we compare these spacecraft to the concept of intergalactic travel, the contrast isn't a failure, it's a measure of how vast the universe truly is. Every increase in speed, every step forward in propulsion, is a small but meaningful victory against the imaginable scales of time and space that surround us. We're learning to walk in a cosmos where we'll one day dream of running. Still, when you take the raw numbers and project them forward, the challenge becomes almost poetic in its impossibility. Even if we could increase Parker Solar Probe speed by 1,000 times, it would still take tens of millions of years to reach Andromeda. And if we increased it by 1,000,000 times, still far slower than light, it would take thousands of years. Those figures remind us that the barrier we face is not just technological, but physical. The universe's ultimate speed limit, the speed of light itself. So as we stand on our small planet, sending fragile machines into the vastness, we find ourselves at the beginning of a story that's still unfolding. We've barely dipped our toes into the cosmic ocean, and yet our spacecraft have already traveled farther than anything built before us. The speeds we've achieved are extraordinary, but they also highlight the magnitude of what lies ahead. And with that foundation, the next step in our journey is to take these speeds, the real measurable velocities of our fastest machines, and calculate what they would actually mean if we tried to use them to reach Andromeda. The results are staggering, and they reveal just how vast the differences between what humanity can currently achieve and the immensity of intergalactic travel. Using the actual speeds of our fastest spacecraft and imagining for a moment that one of them could be sent on a straight, uninterrupted course towards Andromeda and somehow keep its top velocity forever, the travel times become brutally clear. The distance to Andromeda is about 2.5 million light-years, which works out to roughly 2.365 times 10 to the 19 kilometers. If a Voyager-class probe, Voyager 1's approximate velocity of 61,000 kilometers per hour, were launched and could insist on traveling at that speed the whole way, it would need on the order of 44 billion years to arrive. That's about 3 times the current age of the universe, so in practical terms, Voyager 1 would never reach Andromeda. The universe would age far beyond its present form long before the probe made significant progress. A New Horizons-like craft, at roughly 58,000 kilometers per hour, fares only slightly worse. Its one-way journey would be measured in the neighborhood of 46 billion years. Those are astronomical timescales in the truest sense, numbers so huge they scramble ordinary intuition. Now consider the Parker Solar Probe, our record holder for raw speed. During its closest approaches to the Sun, it has reached speeds around 700,000 kilometers per hour. If you take that phenomenal number and apply it to a direct course towards Andromeda, without worrying about the engineering impossibilities of keeping that solar perihelion speed on a straight intergalactic trajectory, the travel times drop dramatically compared with Voyager, but it still remains cosmic, roughly 3.9 billion years. That's roughly comparable to the timescale on which the Milky Way and Andromeda are expected to collide, about 4 billion years. Even with the fastest human-made object we've built so far, the trip would still span timescales comparable to the lifetimes of stars and far beyond the span of a human civilization. Those numbers assume constant top speed with no need for acceleration, deceleration, navigation corrections, or mid-course maneuvers, and they ignore the massive practical problems of energy, shielding, and communications. They also assume the craft could be engineered to survive untouched for billions of years, an impossible expectation with any current hardware. Components fail, power sources decay, cosmic rays and micrometeoroids cause damage, and any onboard tape, chip, or structure will degrade in ways we do not yet know how to prevent over such durations. Even the most robust interstellar probe we can imagine today would not retain function for more than a small fraction of these timescales. Putting these travel times side by side with the age of the universe sharpens the point. The cosmos is about 13.8 billion years old. Voyager-class travel to Andromeda would require a multiple of that age. New Horizons is similar. Parker's extreme speed brings the duration down to billions of years, but still doesn't rescue the voyage into any time frame useful for human explorers. In short, with present propulsion technology, the gulf to another galaxy is effectively insurmountable. We can send signals that cross the solar system, and we can fling tiny probes out into interstellar space, but sending anything, human or robotic, to another galaxy is beyond our current reach. There are other practical consequences to these vast durations. Communication delay would grow incomprehensibly large. If a probe somehow survived and sent back data, those signals would take millions of years to reach Earth, so the mission and its controllers would be separated by entire epochs. The probe would need an independent, self-repairing intelligence to carry out scientific objectives. The concept of mission control becomes meaningless when the round-trip light time is measured in millions of years. Power is another thorn. Radioisotope power systems and solar arrays age and fail. No present power source could keep instruments alive for the millions or billions of years implied here. There are also hazards that accumulate with time. Even at cruising speeds many orders of magnitude below light speed, collisions with interstellar or intergalactic gas and dust are problematic when integrated over billions of years. Erosion, cumulative impacts by even submicroscopic particles, and the gradual bombardment by high-energy cosmic rays would degrade materials and electronics inexorably. Designing a vehicle to survive that relentless slow erosion for billions of years is a different engineering challenge from anything we faced. To place these conclusions in perspective, it helps to consider some middle ground. If humanity could someday build propulsion systems orders of magnitude faster than anything we have now, travel times could shrink from tens of billions or billions of years to millions or hundreds of thousands of years. Still enormous, but slightly less absurd. But with our current hardware, the Voyagers, New Horizons, Parker, and similar craft, the honest conclusion is that reaching Andromeda would take timescales that render the mission effectively impossible for any present civilization acting in any meaningful human timeframe. So measured against today's engineering, the Andromeda voyage is not merely difficult, it is astronomically, categorically out of reach.
That is not a pessimistic statement about curiosity or long-term ambition. It's a clear, quantitative boundary that tells us where current technology stops being relevant and where new physics or dramatic breakthroughs would be needed if intergalactic travel is ever to be more than a dream. For now, these calculations teach humility. Our fastest machines are masterpieces, but the universe is vaster than even those masterpieces can bridge. When we pause to truly reflect on these staggering travel times, the enormity of the challenge becomes almost poetic in its hopelessness. The cold, hard math shows that even our most advanced spacecraft, with their blazing speeds and cutting-edge engineering, would take billions or even tens of billions of years to cross the gulf between the Milky Way and the Andromeda Galaxy. To put that in perspective, that's longer than the age of the universe itself, which has existed for only 13.8 billion years. In other words, even if Voyager 1 had been launched at the dawn of time, racing outward at its current velocity, it wouldn't have made it even a fraction of the way to Andromeda. It would still be wandering through the inky darkness of intergalactic space, its lonely signal to never reach another world.
When we consider the journey to Andromeda through the lens of current technology, the conclusion is clear. It's not a journey we can make. Not now, not in 1,000 years, perhaps not ever, unless our understanding of physics itself evolves. The gulf between galaxies is a reminder of how vast the universe truly is, and how small we are within it. But it's also a reminder of why we keep asking questions like this one. The impossibility of the task doesn't stop us from dreaming. It's what drives us to keep reaching, to keep pushing, to keep trying to turn the unimaginable into the achievable. The human story has always been one of confronting the impossible. Once, crossing an ocean seemed unthinkable. Then, touching the moon did too. The Andromeda Galaxy may lie far beyond our grasp today, but it stands as the ultimate frontier, a challenge that dares us to imagine technologies and futures that stretch beyond our current reality. Before we even dream of crossing that gulf, though, we must first understand what kinds of advanced propulsion methods might one day make it even remotely conceivable.
When faced with the sheer impossibility of reaching another galaxy using today's propulsion systems, the human imagination naturally begins to search for alternatives. We refuse to stop at the limits of what is possible. We speculate about what could be. Over the decades, scientists, engineers, and science fiction thinkers alike have proposed a range of hypothetical propulsion methods that might someday allow us to traverse interstellar and perhaps even intergalactic distances at much greater speeds. While none of these ideas are close to being realized, they offer glimpses of a future where the boundaries of space travel are stretched far beyond our current comprehension. Among the most promising of these concepts is the nuclear fusion drive. Fusion, the same process that powers the stars, involves fusing light atomic nuclei, such as hydrogen isotopes, to release enormous amounts of energy. Unlike traditional chemical rockets, which rely on burning fuel to produce thrust, fusion releases energy millions of times more efficiently. The idea is simple in theory, but staggering in practice. A spacecraft powered by a controlled fusion reactor could continuously accelerate for months or years, gradually building up immense velocity. Projects like Project Daedalus, proposed in the 1970s by the British Interplanetary Society, envisioned an unmanned probe driven by pellets of deuterium and helium-3 ignited by electron beams. According to the design, such a craft could potentially reach about 12% of the speed of light, fast enough to travel to the nearest star, Proxima Centauri, in roughly 40 years. If that kind of propulsion could somehow be scaled up and maintained for intergalactic distances, it could, in theory, reach the Andromeda Galaxy in about 20 million years. That's still an unimaginable amount of time, but compared to the tens of billions of years required by our current spacecraft, it's an extraordinary leap forward, shrinking the journey by a factor of thousands. Taking the concept even further, some scientists have proposed antimatter propulsion, one of the most efficient forms of energy release possible under known physics. When matter and antimatter meet, they annihilate each other completely, converting their entire mass into pure energy, according to Einstein's equation, E equals mc squared. Just 1 gram of antimatter reacting with 1 gram of matter would release the same energy as the atomic bomb that destroyed Hiroshima. Harnessing this reaction for propulsion would allow for near light speed travel. A theoretical antimatter engine could, in principle, achieve speeds approaching 90% of the speed of light, though the engineering challenges are staggering. Producing and storing antimatter in sufficient quantities is currently beyond human capability. The amount we can create today is measured in nanograms, and keeping it stable without it coming into contact with matter is another monumental challenge. Still, the concept tantalizes scientists because it represents the closest thing we can imagine to a truly efficient, relativistic propulsion system. At 90% of light speed, the Andromeda Galaxy could theoretically be reached in just under 3 million years from an outside observer's perspective. A blink of an eye on cosmic timescales, but still an eternity for human civilization. Another elegant idea comes in the form of light sails or solar sails, which use radiation pressure from light to generate thrust. The concept is deceptively simple. Instead of burning fuel, a spacecraft unfurls a massive, ultra-thin reflective sail that catches photons from the sun or from a powerful laser array. Each photon imparts a tiny push, and over time, these countless microscopic nudges build up to substantial speeds. While traditional solar sails rely on sunlight, more advanced proposals, such as the Breakthrough Starshot initiative, suggest using immense ground-based lasers to propel small, lightweight probes to around 20% of the speed of light. At that velocity, a probe could reach Proxima Centauri in about 20 years, an astonishing leap compared to the tens of thousands of years required by Voyager-like craft. If this technology were scaled up for larger interstellar missions, it could, in theory, reach the Andromeda Galaxy in about 12 million years. That's still far beyond any human lifetime, but it represents an extraordinary improvement in our conceptual ability to traverse the stars. Beyond these, there are even more speculative ideas, ones that push into the very edge of theoretical physics. Concepts like ramjet drives, which would collect interstellar hydrogen and fuse it as fuel while traveling, or beam-powered propulsion, which uses energy transmitted from a distant source to drive a spacecraft, could potentially sustain acceleration indefinitely, allowing speeds far closer to light. Then there are photon rockets, which would directly emit light as thrust, extraordinarily efficient, but requiring immense energy sources, possibly entire stars, or artificial power plants of godlike scale. Of course, all of these methods share one thing in common. They are theoretical. Each faces enormous technological, material, and energy challenges that we have not yet come close to solving. Fusion reactors remain difficult to sustain even here on Earth for more than a few seconds. Antimatter cannot be produced or stored safely in usable quantities. Laser sail technology demands power levels and precision engineering orders of magnitude beyond our current capabilities. But while none of these are realistic options today, they serve a vital purpose. They remind us that the limitations we face are not necessarily permanent. Every major breakthrough in human history once seemed impossible. There was a time when powered flight, space travel, and even the idea of landing on the moon were little more than fantasies. The hypothetical propulsion systems of today may be the reality of the distant future. Even if it takes centuries, the seeds of possibility are already planted. Scientists continue to experiment with fusion, study antimatter interactions, and test solar sail prototypes, each step bringing us a fraction closer to understanding how we might one day move between the stars.
The power of these ideas isn't just in their scientific potential. It's in what they represent for humanity's imagination. They embody our refusal to accept the boundaries of the known universe. They tell us that even when faced with the immensity of space and the apparent impossibility of reaching another galaxy, our instinct is not to give up, but to ask, what if? And so, as we turn our gaze toward the Andromeda Galaxy and dream of journeys across the intergalactic void, these hypothetical propulsion systems become our bridge between reality and imagination, stepping stones across the impossible. The next logical question is, even if such advanced propulsion systems did exist, how much faster could they really take us? What kind of timescales would we be dealing with then? Millions instead of billions of years? That's the next question to explore, and it brings us closer to the heart of what future space travel might truly look like. If we allow ourselves to imagine that one or more of the advanced propulsion ideas we just discussed actually became real, the gulf to Andromeda suddenly shrinks from an effectively infinite wall to a long, painful road, measured not in tens of billions of years, but in millions. That's still far beyond any human lifetime or civilization timescale we comfortably plan for, but it's a different kind of impossibility. One that invites engineering, infrastructure, and patient, epic-spanning projects instead of outright violation of physics. Let's run through realistic order estimates for a handful of plausible advanced systems and then look at the engineering and mission realities that make even those millions of years numbers arguably optimistic. Start with a credible fusion-driven design, a carefully engineered fusion rocket that could produce continuous high-thrust acceleration for long periods, something along the lines of historical proposals such as Project Daedalus, might be able to reach a stable cruise fraction of light speed on the order of 10 to 15% of c. At 12% of light speed, the simple external frame travel time to cover 2.5 million light-years is on the order of 20 million years. That's an enormous span, but in cosmic terms, it's a dramatic improvement over tens of billions of years. It's still a mission that would outlast entire civilizations, but it would be conceivable as a one-way robotic endeavor if the engineering, manufacturing, and energy infrastructure existed to build and launch it. Light sail concepts scale differently depending on mass and the amount of beam power available. A small, wafer-scale probe pushed by an enormous ground or space-based laser array, the kind of scheme popularized in recent decades for nearby star missions, could, with extreme engineering, approach a few tenths of the speed of light. A commonly discussed optimistic target is 20% of c. At 0.2 c, the transit time to Andromeda is roughly 12.5 million years as measured in the external rest frame. That's still millions of years, but it moves us from geological to near-geological timescales, rather than cosmological ones. If the sail could be scaled to larger payloads, which carries huge additional challenges, similar orders of magnitude apply. Everything gets measured in millions of years rather than billions. Antimatter engines sit at the far end of the theoretical spectrum because of their extreme energy density. If, hypothetically, antimatter production and storage problems were solved, and an engine could convert a sizable fraction of annihilation energy into directed thrust, cruise velocities could conceivably approach relativistic speeds like 0.9 c or higher. At 90% of light speed, the external frame travel time is roughly 2.8 million years. That's a very different number. It turns Andromeda from virtually forever into something that, while still staggeringly long, sits within a range where time-dilated human passengers, if we were ever able to protect them from other effects, would experience significantly less subjective time. But achieving and sustaining 0.9 c for a macroscopic mission payload, dealing with acceleration forces, radiation, shielding, and the colossal energetic costs, remains wildly speculative with our current knowledge and capabilities.
It's important to note the difference between the time measured by outside observers and what travelers might experience at relativistic speeds. If a vehicle could cruise at, say, 99% of the speed of light, the outside frame travel time to Andromeda is roughly 2.525 million years. But because of relativistic time dilation, the proper time experienced aboard the vessel would be shorter by a factor determined by gamma. At 99% c, the Lorentz factor is about 7. So the crew's subjective elapsed time would be on the order of 350,000 years. That still exceeds the span of recorded human history many times over, but it demonstrates that near-light travel changes the human perceived duration dramatically. At even higher fractions of c, the traveler's proper time can shrink into the tens of thousands of years. Still long, but in principle more human scale than millions. The flip side is that the energy and engineering demands to reach those fractions of c explode, and the hazards from interstellar and intergalactic particle fluxes and radiation become far more acute. Beyond point-to-point transit speed, real mission architectures add complexity that lengthen effective travel times.
No practical ship accelerates instantly to cruise speed and then simply appears at its destination. You must accelerate, coast, and decelerate. For a multi-million-year voyage, low-thrust continuous acceleration designs, where the craft slowly builds up velocity over centuries or millennia and later decelerates by the same process, are feasible in principle but require long acceleration phases that increase total mission elapsed time from distance divided by cruise speed by a factor that depends on acceleration profile. High-thrust, short-burst acceleration is energetically brutal and mechanically extreme. Low-thrust, long-duration schemes are gentler, but spread mission timelines out. Either way, the simple distance divided by speed is a baseline. The real mission will take longer. There are also pragmatic designs that sidestep the need to carry all energy and fuel on board. Beam-driven sails and staged laser or particle beam propulsion push the energy source off the ship and place it back on the origin, or on a network of relay stations. That reduces the vehicle mass enormously and permits higher cruise speeds for tiny probes. But building and powering the required beamer arrays would require energy production and global or interplanetary industrial scales beyond anything yet constructed. Those arrays themselves would need to last and be maintained over centuries to millennia as they propel interstellar missions. For a mission to Andromeda, the beamer durations and precision would have to be orders of magnitude greater than for nearby star missions, which raises the question of societal continuity. Could a civilization sustain the economic and social will to build and maintain such infrastructure for the centuries it takes to accelerate even small probes to meaningful fractions of light speed? Robotic strategies open additional options that change the flavor of time to reach. Self-replicating probes, von Neumann machines, could land on intermediate star systems, use local resources to replicate, and send further probes outward in an exponential wave. On galactic scales, this can dramatically shorten the effective time it takes for a civilization's presence, or its probes, to spread. But between galaxies, the number density of useful targets is vastly lower, and the distances between usable resource sites are much larger. The replication approach could still shave time compared with a single monolithic craft, but it requires autonomous manufacturing, robust repair, and a tolerance for evolutionary drift in the probe's software and hardware across many replications. Estimates for intergalactic colonization waves are highly speculative, but the general result is that even with replication, you're likely still looking at millions to tens of millions of years to reach Andromeda, unless ships routinely operate at very large fractions of sea.
Then there's the question of survivability and mission utility. For robotic probes, lower mass often means easier acceleration and dramatically lower energy budgets. So the sweet spot for early attempts at very distant missions could be tiny, automated probes designed to survive long durations via redundancy, self-repair, and minimal moving parts. Such probes would still need robust shielding against the cumulative micrometeoroid and high-energy particle damage accrued over millions of years. Human missions, by contrast, face nearly insurmountable biological and societal challenges if mission durations span thousands or millions of years, even setting aside relativistic dilation benefits. Generational ships, suspended animation, and closed-loop biospheres are the stuff of fiction and long-range engineering proposals, but their viability over millions of years is essentially zero without completely revolutionary advances in life support and societal stability. Finally, remember that reaching Andromeda isn't only about transit time. Even if an advanced propulsion system could shorten crossing time to a few million years, communications back to Earth would be delayed by millions of years one way. Any data returned is information about a civilization and environment displaced in time by that same gulf. The human concept of mission control disappears. Any intergalactic mission would need an enormous degree of autonomy and a robust mission philosophy that accepts we will not receive timely feedback. So, in rough summary, with plausible near-future breakthroughs scaled up immensely, transit times could fall into the range of tens of millions down to a few million years. Fusion drives and scaled-up light sail concepts plausibly sit in the tens of millions of years. Ambitious beam-driven sails and optimized fusion or antimatter systems could reduce that to low millions.
Approaching 0.9 C or above, antimatter, or as yet unknown physics, could potentially get you into the couple million-year bracket as measured externally, and into far shorter subjective times for relativistic travelers. None of these scenarios makes the journey comfortable or trivial, but they transform the scale from cosmological impossibility to epical engineering challenge. That shift is meaningful. It reframes the problem from one of fundamental unreachability to one of extraordinary investment, revolutionary engineering, and societal commitment across timescales that dwarf nations and civilizations. Einstein's theory of relativity introduced one of the most profound and immutable truths in all of physics. Nothing with mass can ever reach, let alone exceed, the speed of light in a vacuum. This single concept forms the ultimate speed limit of the universe, a boundary written not by engineering constraints, but by the fundamental fabric of reality itself. To understand why this is true and why it places such a colossal barrier before our dream of reaching distant galaxies like Andromeda, we must step back and explore the nature of space, time, and energy as Einstein revealed them to be. Before Einstein, most scientists thought of space and time as separate, absolute entities, a kind of static stage upon which the universe unfolded. Newtonian physics treated them as fixed backdrops. Space was the same everywhere, time ticked uniformly for everyone, and speeds simply added together. But Einstein's special theory of relativity, published in 1905, shattered that picture. He showed that space and time are not independent. They are woven together into a single four-dimensional continuum called space-time, and how you experience both depends on your motion relative to everything else. At the heart of relativity lies a simple but astonishing postulate. The speed of light is constant, the same for all observers regardless of their motion or the motion of the light source. Whether you are standing still, hurtling through space at half the speed of light, or riding alongside a photon beam, if such a thing were possible, light will always appear to move away from you at 299,792 kilometers per second, or about 186,282 miles per second. This universal speed limit defines the structure of space-time itself. It's not that light is fast within space and time, it's that light speed is the cosmic measuring stick by which space and time adjust themselves. Now, here's where it gets both fascinating and restrictive. According to Einstein's equations, as an object with mass accelerates closer to the speed of light, several extraordinary things happen. First, its relativistic mass increases, meaning it takes more and more energy to keep accelerating it. Second, time slows down for that object relative to an outside observer, a phenomenon known as time dilation. Third, length contraction occurs, meaning that in the direction of travel, distances appear to shrink. These effects are not theoretical curiosities. They have been experimentally verified countless times, from particle accelerators to atomic clocks flown on aircraft.
But the key consequence for space travel is this. As an object's speed approaches the speed of light, its mass effectively becomes infinite, and therefore the energy required to accelerate it further also approaches infinity. No amount of propulsion, no conceivable engine, no quantity of fuel can supply infinite energy. The closer you try to get to light speed, the harder it becomes to gain even the smallest incremental increase in velocity. It's like pushing against an invisible wall that stiffens with every effort. At 90% of light speed, your energy requirements have already skyrocketed. At 99%, they are astronomical. At 99.9999999% of light speed, the energy needed is so immense, it rivals the total output of galaxies. This immutable law, the cosmic speed limit, is why intergalactic travel remains such a daunting challenge. Even if humanity developed a propulsion system capable of generating colossal amounts of thrust without fuel constraints, physics itself would draw the line. We can approach the speed of light asymptotically, getting ever closer but never quite touching it. The photons that make up light are massless, which is why they can move at that ultimate velocity. But anything made of matter, no matter how small, is permanently barred from joining them. Einstein's insight also reveals why the universe looks the way it does. The speed of light doesn't just limit how fast we can travel, it also defines how we perceive the cosmos. When we look out into the night sky, we're not seeing the universe as it is now, but as it was in the past. The light from the sun takes about 8 minutes to reach Earth. The light from the nearest star, Proxima Centauri, takes more than 4 years. And the faint glow of the Andromeda Galaxy that graces our telescopes tonight left that galaxy roughly 2.5 million years ago. Every distant object in the sky is a time capsule, a window into a different epoch of cosmic history. This perspective underscores how deeply the speed of light shapes not only travel, but also perception. It defines the ultimate horizon of our knowledge. No signal, no ship, no information can cross that threshold faster than light. Even communication with a hypothetical probe traveling near that speed would be agonizingly delayed, taking millions of years to reach across intergalactic distances. It's worth noting that many proposed faster-than-light ideas, warp drives, wormholes, or hypothetical tachyons, all depend on ways to bypass the laws of relativity rather than break them outright. They suggest bending space-time rather than moving through it faster than light. Because according to relativity, it isn't space itself that's forbidden from stretching or warping faster than light. It's objects within space that cannot locally exceed that speed. This is why the universe itself can expand faster than light. Galaxies can recede from us faster than light not because they're moving through space at superluminal speeds, but because the space between us is stretching. So relativity doesn't simply say, you can't go fast. It says the universe has a speed woven into its fabric, and this speed defines the relationship between space, time, and energy. The closer you approach that speed, the more reality itself begins to distort around you. Space contracts, time stretches, and energy needs soar. The cosmic speed limit is not an arbitrary rule, it's a reflection of how existence itself is structured. This understanding transforms the dream of intergalactic travel, from one of raw propulsion into one of new physics. To reach Andromeda in less than millions of years, we would need to find a way not to go through space faster than light, but to go around it, to manipulate space-time itself. That's where speculative concepts like warp drives and wormholes begin to enter the discussion, not as violations of relativity, but as creative reimaginings of what it might allow if we could harness its deeper geometry. But before we venture into those realms of theory, it's worth pausing to appreciate what Einstein gave us: a universe where speed, time, and space are inseparably linked. His equations may have closed the door on faster-than-light travel for now, but they also opened our eyes to a deeper truth: that the cosmos is not a static void, but a dynamic, interconnected tapestry. In understanding the limits, we've also uncovered the grandeur of the universe itself. If we could somehow break free from the painfully slow crawl of our current spacecraft and reach speeds that are even a meaningful fraction of the speed of light, the nature of interstellar and intergalactic travel would change completely. At these incredible velocities, 10%, 50%, 90% of light speed, the distances that today seem infinite would begin to contract, both literally and figuratively. The impossible would still be difficult, but not hopeless. And in these ranges, the fascinating effects predicted by Einstein's relativity, time dilation, length contraction, and the warping of perception begin to dominate, transforming how both the travelers and outside observers experience the journey.
Let's begin modestly, with 10% of the speed of light, or about 30,000 kilometers per second, roughly 67 million miles per hour. This is still unimaginably fast by human standards. A spacecraft moving at that velocity could circle Earth 7 times in a single second. Yet, even at this breathtaking speed, the Andromeda Galaxy would remain unimaginably far away. Since Andromeda lies 2.5 million light-years from us, a ship traveling at 1/10 light speed would take roughly 25 million years to get there, as measured from an outside observer. That's shorter than the time it took for primates to evolve into humans on Earth, but it's still a time span so vast that entire species, ecosystems, and civilizations would rise and fall before the journey was complete. For the crew on such a vessel, time dilation, though present, would be minimal at 10% of light speed. Their clocks would tick only a tiny bit slower than those on Earth, meaning they would still experience nearly the same 25 million years of passage. So even though the universe would barely change around them, the travelers themselves would never live to see their destination. Now increase the speed to 50% of the speed of light, 150,000 kilometers per second. This is where relativity begins to show its power in reshaping how motion is experienced. At half the speed of light, the time dilation factor, known as gamma, becomes about 1.15. That means time on the ship runs around 15% slower than for observers back home. For every 100 years that pass on Earth, only 87 years pass for the crew. It's not yet dramatic, but it's noticeable. The travel time to Andromeda, as measured from Earth, would drop to about 5 million years. Still enormous, but 5 times shorter than at 10% light speed. For the travelers, because of their time dilation, the trip might feel a bit shorter, perhaps around 4.3 million years. At these speeds, the journey takes on a strange dual nature. From the outside, the ship appears frozen in time, creeping slowly toward its goal over millions of years. But inside, the crew's clocks tick at a slightly different rhythm, their lifetime stretched relative to those they left behind. They would be moving through a reality subtly distorted by motion itself, their mass slightly greater, their view of the stars warped ahead of them by the compression of space. But the truly astonishing changes appear when we push into the realm of 90% of the speed of light, about 270,000 kilometers per second. Now, relativity becomes the dominant force shaping the experience of travel. The time dilation factor jumps to about 2.29. That means for every 2.29 years that pass on Earth, only 1 year passes for the travelers. Space itself, in the direction of motion, begins to contract significantly from their perspective. To them, the vast distance to Andromeda, 2.5 million light-years as measured from Earth, would appear shrunk to only about 1.1 million light-years due to length contraction. From the perspective of observers on Earth, the journey would still take around 2.78 million years. But for the travelers on board, the subjective experience would be drastically different. Thanks to time dilation, they would experience only about 1.2 million years passing on their ship. That's still longer than any human could live, but it's more than twice as fast as external observers would perceive. At this velocity, the crew would witness the outside universe rushing past them at incredible intensity. The starlight ahead would be blue-shifted, compressed into higher frequencies, while the light behind them would redshift into deeper and deeper wavelengths. The front of their ship would face a relentless bombardment of high-energy cosmic radiation, posing lethal risks that would require extraordinary shielding. At 90% of light speed, the stars ahead would also seem to cluster and distort, appearing to squeeze into a narrow tunnel of light, an effect known as the relativistic aberration. Space itself would seem to collapse into a glowing, dazzling tunnel in the direction of travel, while darkness would stretch infinitely behind. The perception of direction, color, and even the flow of time would change. Inside the ship, time would slow, distances would contract, and energy demands would soar to unimaginable levels. If we dare to go even further, 99% of the speed of light, relativity begins to produce mind-bending consequences. The time dilation factor climbs to about 7. That means for every 7 years that pass on Earth, only 1 year passes for the travelers. The 2.5 million light-year journey to Andromeda would take about 2.53 million years in the external frame, but to the crew, only 360,000 years would elapse. For the first time, we begin to see a scenario where the traveler's perception of time falls into a range that, while still vast, is shorter than the lifespan of many species on Earth. Of course, the energy required to reach and maintain 99% of light speed would be utterly beyond anything humanity can produce, but it shows the tantalizing power of relativistic effects. The closer you approach the speed of light, the slower your clock runs relative to the universe around you. In a sense, motion gives you the power to step outside of time, to watch the cosmos evolve faster than you do. For travelers racing toward Andromeda at 99.999% of light speed, by the time they arrive, millions of years would have passed on Earth. The continents would have shifted, species would have evolved or vanished, and perhaps the Milky Way and Andromeda would already be colliding. To those travelers, their journey would have taken a few thousand years,
but they would arrive in a completely different universe.
This is the paradox of near-light travel. It brings the unreachable within personal reach, yet separates the traveler irreversibly from the world they left behind. It's a reminder that even if we someday learn to fly close to light speed, the universe would still demand a price, not in money or fuel, but in time itself. The closer a traveler moves toward the speed of light, the more deeply they begin to experience one of the strangest and most beautiful consequences of Einstein's relativity: time dilation. It is not a trick of perception, not a distortion caused by machinery or illusion, but a real physical effect written into the structure of the universe itself. Time, that constant and invisible river we all drift through, begins to flow at different rates for different observers, depending on their motion. And when you begin to approach the speed of light, that river stretches and slows so dramatically that a few years for the traveler can correspond to thousands, even millions of years for those they left behind. Imagine a starship accelerating steadily toward a distant galaxy like Andromeda, gradually nearing a significant fraction of light speed. To those watching from Earth, its progress would seem painfully slow. Decades would pass, then centuries, then millennia, and still the ship would appear to crawl across the void, its light redshifting as it receded. Yet for the crew aboard that ship, time would feel perfectly normal. Their hearts would beat in rhythm, their clocks would tick as usual, their conversations would flow naturally. Nothing in their immediate environment would feel strange, and yet in the universe beyond, eons would be unfolding. Civilizations might rise, fall, and be forgotten, while the travelers themselves experienced only a few short years of life. This phenomenon is the essence of time dilation. As an object's velocity increases toward the speed of light, the passage of time for that object slows relative to a stationary observer. The faster it moves, the greater the effect. At everyday speeds, cars, airplanes, even spacecraft, the difference is so minuscule it's imperceptible. But once you start moving at a significant fraction of light speed, the effect becomes enormous. Consider what happens at 90% of light speed. The time dilation factor, known as gamma, equals about 2.29. That means that for every 2.29 years that pass on Earth, the travelers experience only 1 year. If the journey to Andromeda takes 2.5 million years from Earth's perspective, the crew would feel only about 1.1 million years passing. Still an impossible duration for a human lifespan, but a demonstration of how the flow of time itself can be stretched and manipulated simply through motion. Now push that speed higher. At 99% of the speed of light, the gamma factor rises to about 7. That means for every 7 years on Earth, 1 year passes for the travelers. At 99.9999% of light speed, the factor explodes to roughly 700. For every 700 years that pass in the outside universe, only 1 year elapses for those aboard the ship. Suddenly, what seems like a journey of millions of years for those watching from afar becomes a voyage lasting mere thousands or even hundreds of years from the traveler's own perspective. This isn't science fiction. It's a mathematically proven and experimentally verified reality. Particle physicists see it every day in laboratories around the world. Subatomic particles, known as muons, for example, normally decay in microseconds when at rest. But when they are accelerated to near light speeds in particle accelerators, their internal clocks slow so drastically that they survive hundreds of times longer than they would otherwise. The same principle would apply to humans. If we could travel that fast, we too would experience time slowing in our own frames of reference. But this slowing of time comes at a cost, a profound separation between the traveler and the world they leave behind. If a spaceship departed Earth today and accelerated to 99.999% of light speed, the crew might reach Andromeda in what feels to them like just 3,600 years. But when they arrived, more than 2.5 million years would have passed on Earth. By then, our species might have evolved into something entirely different. Our cities long vanished, our oceans reshaped, and the very constellations unrecognizable. The crew would emerge into a future so distant that the world they left behind would exist only in the echoes of cosmic history. This is the emotional and philosophical dimension of time dilation. It's not just a scientific curiosity, it's a reminder that time itself is not absolute. For travelers moving near the speed of light, the universe becomes both smaller and older. The stars ahead contract closer together, the journey shortens, and yet the rest of existence races forward into the future. To go fast enough to make the universe seem within reach, you must surrender your connection to the time in which you were born. From the traveler's viewpoint, this would create surreal experiences. The Andromeda Galaxy, which normally lies 2.5 million light-years away, would seem dramatically closer due to length contraction, another relativistic effect where distances shrink in the direction of motion. The faster the ship moves, the more compressed space becomes ahead of it. The crew would see the cosmic background shift into brilliant hues. Starlight in front would blue shift into higher frequencies, while everything behind would fade into a dim red haze. And though their onboard clocks would continue to tick at their normal rhythm, the universe outside would be rushing through ages. Galaxies would evolve, stars would be born and die, and entire cosmic epochs would unfold in what felt like moments. If such a journey ever became possible, time dilation would redefine what we mean by travel. The ship's crew might depart Earth as explorers, but by the time they reach their destination, they would be more like time travelers, witnesses to a universe millions of years older than the one they left. From Earth's perspective, they would have vanished long ago. From theirs, the journey would feel like a single, continuous experience. They would exist between times, moving through space while slipping ever further from the temporal reality of their origin. This duality, the separation of personal time from universal time, is one of the most humbling insights of relativity. It reveals that time, so familiar and constant in our daily lives, is not a universal metronome ticking the same for all. Instead, it's a flexible dimension, stretching and bending in response to motion and gravity. The faster we move, the slower our time flows relative to the rest of the universe. And therein lies both the beauty and tragedy of near light-speed travel. On one hand, it offers a tantalizing solution to the problem of cosmic distances. With enough speed, the vastness between galaxies could be compressed into humanly meaningful spans. On the other, it severs travelers from their own time, from their home, their history, their species. They would reach Andromeda, yes, but they would do so as strangers in a universe that no longer remembers them. Time dilation is, in many ways, the universe's most poetic paradox. It gives travelers a glimpse of eternity while costing them everything familiar. It says, you can cross the stars, but you can never truly go home. When we reach the limits of what physics currently allows, when the reality of millions or billions of years of travel renders the dream of intergalactic exploration almost absurd, our imagination naturally seeks loopholes in the cosmic rulebook. If no object with mass can ever reach the speed of light, then perhaps, some scientists and visionaries suggest, the solution is not to go through space faster, but to go around it. This line of thinking has given rise to some of the most fascinating and speculative ideas in theoretical physics. Wormholes, warp drives, and other exotic mechanisms that would, in essence, bend space-time itself to shorten the journey. These concepts push beyond the edge of what is currently testable, but they are grounded in legitimate extensions of Einstein's equations, beautiful possibilities that hint that the universe might be stranger and more flexible than we dare to imagine. Let's start with wormholes, also known as Einstein-Rosen bridges. In the simplest terms, a wormhole is a hypothetical tunnel that connects two distant points in space-time. Imagine space not as a vast empty expanse, but as a two-dimensional sheet of fabric. If you draw two dots on opposite ends of that sheet and fold it so the dots touch, you've created a shortcut, a bridge between two locations that bypasses the normal distance between them. A wormhole, theoretically, would function like that fold on a cosmic scale,
linking distant parts of the universe, perhaps even two galaxies, through a hidden corridor outside conventional space. Einstein's general theory of relativity allows for the mathematical existence of wormholes. His field equations, when solved under certain extreme conditions, produce spacetime geometries that could resemble tunnels. These solutions were first proposed by Einstein and his collaborator Nathan Rosen in 1935, hence the term Einstein-Rosen bridge. Later physicists like Kip Thorne and others expanded on these ideas, suggesting that if such tunnels existed and could be stabilized, they might allow instantaneous travel between points separated by vast cosmic distances. However, the key word is if. Wormholes, while mathematically consistent, would be inherently unstable. They would collapse the instant anything tried to pass through them, unless something could hold them open. That something would have to be a form of matter with negative energy density, often called exotic matter. Unlike normal matter, which exerts positive energy and gravitational attraction, exotic matter would have the opposite effect. It would repel, preventing the wormhole from pinching closed. While negative energy does appear in certain quantum effects, such as the Casimir effect, there's no known way to generate or sustain it in the quantities required to stabilize a traversable wormhole. Even if we could somehow stabilize one, the engineering challenges are staggering beyond imagination. A wormhole large enough for a spacecraft would have to exist at astronomical scales and remain stable under enormous gravitational stresses. And even if such a structure could be created or discovered, entering or exiting it might expose travelers to forces, radiation, and quantum effects so extreme that survival could be impossible. Still, the concept remains one of the most tantalizing in physics, because if wormholes were real and traversable, they could connect not only distant galaxies, but perhaps even different universes, creating a cosmic network of shortcuts through space-time itself.
The second major theoretical concept is the warp drive, most famously represented by the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Inspired by science fiction, but rooted in Einstein's equations, Alcubierre's idea was revolutionary. Instead of moving a ship through space, the ship would remain stationary within a warp bubble while space-time itself expanded behind it and contracted ahead of it. In this way, the bubble, and everything inside it, would effectively move faster than light relative to distant observers, even though locally the ship would never exceed light speed. This idea circumvents the main restriction of relativity because it doesn't involve breaking the speed of light within spacetime. It manipulates spacetime itself. The warp drive would, in theory, allow for superluminal travel without violating Einstein's laws. A ship could travel from Earth to Andromeda in weeks or months from the crew's perspective, while bypassing the need for infinite energy to accelerate mass. But the obstacles are monumental. To create and sustain such a warp bubble would require negative energy, the same kind of exotic matter needed for wormholes, in truly cosmic amounts. Early calculations estimated that powering an Alcubierre drive might demand as much energy as converting the entire mass of Jupiter into pure energy. Later refinements suggested more efficient configurations, but even then, the required energy remains beyond anything humanity could dream of producing. Moreover, even if a warp bubble could be generated, serious theoretical problems emerge. It could cause catastrophic radiation buildup at the front of the bubble, annihilating anything upon arrival. And according to some analyses, the bubble might not be able to form without pre-existing faster-than-light conditions, a catch-22 that leaves it purely speculative for now. Still, the warp drive concept captures the human spirit of possibility better than almost any other scientific idea. It takes the unyielding laws of relativity and tries to dance with them, not by breaking the rules, but by reinterpreting them. It suggests that if we ever learn to manipulate spacetime itself, distance may cease to be a barrier. A trip to Andromeda could take minutes instead of millions of years. It is the ultimate dream of cosmic engineering, bending reality to make the unreachable reachable. There are other, even more speculative proposals as well. Ideas like quantum tunneling, where particles appear to cross barriers instantaneously, or the concept of cosmic strings, one-dimensional defects in spacetime that might allow for shortcuts if manipulated. Some physicists have even proposed the existence of white holes, the theoretical opposites of black holes, which could act as exit points for wormholes. These remain deep in the realm of theory. often bordering on the philosophical, but they all stem from one common desire: to find a way to cheat the cosmic distance game. It's important, however, to remember that all these concepts, wormholes, warp drives, space-time manipulation, remain unproven. No evidence currently suggests that traversable wormholes or negative energy fields exist in usable form. They're consistent with relativity's mathematics, but that doesn't mean the universe allows them in reality. Physics often permits elegant possibilities that nature never realizes. And yet, the fact that these ideas can exist within our best theories hints at something profound. The universe might hold secrets that we have only just begun to glimpse. The pursuit of these concepts also highlights a beautiful symmetry between science and imagination. While engineers struggle with rockets and plasma drives, theoretical physicists explore the outer limits of what's possible, asking whether the universe itself might provide shortcuts beyond our technological reach. And in doing so, they remind us that science is not just about what we can do today, it's about what we might one day understand. For now, these theoretical shortcuts are bridges not across space, but across time, between the present moment of our limited understanding and a future where we might command the geometry of the cosmos itself. The idea that we could fold space like paper or write a bubble through the fabric of reality is breathtaking, not because it's easy to believe, but because it reminds us how vast our ignorance still is, and how boundless our curiosity must be to overcome it. When we begin to seriously imagine journeys to destinations as distant as the Andromeda Galaxy, it becomes immediately clear that the question is not simply one of propulsion or distance, it's one of endurance. Even if humanity someday invents propulsion systems capable of traveling at a fraction of light speed, the challenges of sustaining human life across such immense timescales make crude intergalactic missions almost impossible to conceive. For now, and for the foreseeable future, such journeys are far more plausible for robotic probes than for human explorers. Human beings are fragile, complex biological organisms evolved to thrive in the narrow comfort zone of Earth's environment. We need breathable air, food, water, protection from radiation, artificial gravity to prevent muscle and bone deterioration, and psychological stability. Every second of survival in space requires energy, maintenance, and careful control of the environment. Even on the International Space Station, just 400 kilometers above Earth, astronauts depend on constant resupply missions and the unwavering support of mission control. Now imagine maintaining that same delicate equilibrium not for months, but for millions of years. The sheer absurdity of the idea shows how profoundly unsuitable our biology is for intergalactic travel as we currently understand it. Robotic probes, on the other hand, are not limited by lifespan, hunger, or the need for comfort. They don't age, they don't suffer, and they can operate in conditions that would instantly kill a human being. A robot doesn't care about isolation or time, it can drift through space for eons, waiting patiently for its moment to awaken and transmit data. It's this endurance that makes robotic missions the most realistic option for journeys beyond our galaxy. Consider the Voyager probes, launched in 1977. These spacecraft were designed to explore the outer planets of our solar system, yet nearly 5 decades later, they continue to send faint signals from the edge of the interstellar space. They are the farthest human-made objects from Earth, more than 24 billion kilometers away. And though they are only moving at about 17 kilometers per second, they embody the essence of human exploration: persistence and resilience. Voyager 1 will keep drifting through the void long after its power source fails, perhaps for billions of years, silently carrying humanity's message, the famous golden record, into the deep unknown.
Scaling up that concept, we could imagine far more advanced robotic missions built specifically for intergalactic travel. These might be powered by nuclear fusion, light sails, or even AI-driven self-repairing systems that allow them to function for millions of years. A probe launched toward Andromeda wouldn't need to arrive quickly by human standards. It could simply keep going, generation after generation, perhaps waking periodically to check its trajectory, perform maintenance, or gather data from the intergalactic medium. Time means little to machines. Where humans see impossibility, robots see patience. Another crucial advantage of robotic probes is their durability in radiation-rich environments. Space, particularly beyond the protective magnetic bubble of our solar system, is filled with high-energy cosmic rays and interstellar particles that can wreak havoc on organic tissue. For a human, long-term exposure to such radiation would lead to severe health problems and death. Shielding a human spacecraft adequately would require enormous amounts of mass, increasing fuel requirements exponentially. Robots, however, can be hardened with materials that would be impractical for a crewed mission. They can also hibernate for long stretches, minimizing power usage and system degradation. Yet, even robotic missions face immense challenges. Over millions of years, even the smallest malfunctions could accumulate into catastrophic failures. Cosmic dust, micrometeoroids, or simple degradation of components due to atomic-level damage could destroy a probe long before it reached its destination. That's why some scientists have proposed self-replicating or self-repairing probes, often called von Neumann probes, named after the mathematician John von Neumann, who first theorized about machines capable of reproducing themselves. Such probes would gather raw materials from asteroids, planets, or interstellar dust to create copies of themselves, ensuring that even if some were lost, others could continue onward. This concept, while speculative, paints a compelling picture of how intergalactic exploration might actually unfold. Instead of one heroic starship making one single grand voyage, humanity might send out countless tiny, intelligent machines, a swarm of explorers spreading across the universe over millennia, building, repairing, and evolving as they go. These robotic descendants could carry with them the essence of human knowledge, culture, and curiosity, perhaps even digital copies of human consciousness or genetic information. In that way, even if biological humans never set foot in Andromeda, our creations, our extensions, might. Now, when we turn back to the idea of humans making such a journey, the scale of the challenge becomes almost mythic. A human crew traveling to Andromeda, even at relativistic speeds, would face not only the technical problem of maintaining life support, but also the psychological and generational problem of time. Even if a ship traveled at 99.9999% of light speed, and the journey felt like a few thousand years on board, the crew would still live through more time than any human has ever experienced, centuries upon centuries in isolation. Generations would live and die aboard that ship before ever seeing their destination, unless technologies for suspended animation or life extension far beyond anything we know were developed.
The idea of generation ships has long fascinated both scientists and science fiction writers. These are vast, self-contained habitats that could sustain entire societies for thousands of years as they drift through interstellar space. Such a ship wouldn't need to reach Andromeda quickly. It would be a traveling civilization, with farms, cities, and social systems that evolve independently. However, the challenges of building and maintaining such an ecosystem for even a few thousand years, let alone millions, are staggering. Even minor system failures could doom the mission. Social instability, biological collapse, or simple entropy would almost certainly claim such a ship before it ever arrived. Some theorists have imagined cryogenic suspension or digital consciousness transfer as possible solutions, freezing human life until arrival or sending consciousness as information rather than flesh. But both ideas remain speculative, with no proven technology to make them viable. The biological fragility of humans, combined with the enormity of cosmic timescales, makes us ill-suited for journeys that last longer than our species' entire evolutionary history. Robots, on the other hand, already transcend many of these limits. A robotic explorer could function in deep space with minimal energy, powered by starlight, cosmic rays, or onboard fusion. It could think, learn, and adapt. With the rise of artificial intelligence, we may one day design probes that can not only operate autonomously, but also decide their own paths, explore unknown worlds, and send back data that humans cannot yet interpret. In a sense, these probes would be our intellectual offspring, explorers driven not by survival,
but by curiosity. It is therefore not difficult to imagine that the first emissaries from Earth to the Andromeda Galaxy will not be humans in sleek starships, but rather small, durable, intelligent machines, silent ambassadors carrying the legacy of a species that once gazed up at the night sky and wondered what lay beyond. Humanity's first intergalactic footprints will likely be robotic, not because we lack ambition, but because robots are better suited to survive the void. And perhaps, in a way, that's poetic. We may never walk on the worlds of Andromeda ourselves, but our creations could. They might look up at Andromeda stars one day and transmit home, though home, by then, would be millions of years in the past. In that moment, the universe would have witnessed a profound continuity. Machines fulfilling the dreams of their makers, bridging the gap between galaxies when their creators could not. In the grand scale of cosmic exploration, it might not be flesh that travels first, but thought, encoded, enduring, and patient. Humanity's hands may never touch Andromeda, but our mind prints might. The most astonishing twist in this entire cosmic story is that, in a sense, we don't actually need to travel to the Andromeda Galaxy, because one day Andromeda is coming to us. In about 4 billion years, the Milky Way and the Andromeda galaxies will collide and merge, forming an entirely new galactic system. This future event, a slow, graceful dance on a cosmic timescale, is not science fiction or speculation. It is an inevitable consequence of gravity unfolding silently across millions of light years, even as we speak. Every telescope observation, every measurement of Andromeda's motion confirms it. Our nearest galactic neighbor is on a direct collision course with us. Right now, Andromeda is rushing toward the Milky Way at a speed of about 110 kilometers per second, roughly 250,000 miles per hour. That may sound impossibly fast, yet, when measured against the scale of the universe, it's a gentle drift. The two galaxies are like massive cosmic whirlpools, slowly spiraling toward one another across the immense ocean of intergalactic space. Over billions of years, gravity has been pulling them together, and in the distant future, that attraction will culminate in spectacular merger, a transformation that will reshape the night sky and the structure of our galactic home forever. When Andromeda finally draws close enough, the first thing that will change is the sky itself. Future observers on Earth, or whatever descendants of humanity may still exist, will look up to see the Andromeda Galaxy growing larger and brighter with each passing epoch. At first, it will appear as a faint smudge, as it does today. Then, over millions of years, it will swell until it dominates the heavens, its spiral arms stretching wide enough to fill the view. Eventually, its stars will become distinct and visible, filling the sky with new constellations and radiant clouds of light. The night sky will no longer be dark. It will blaze with the light of 1 billion suns. Despite the word collision, the event will not be a violent crash in the way we imagine physical impacts. Galaxies are mostly empty space. The distances between stars are so vast that when the Milky Way and Andromeda pass through one another, almost no individual stars will collide. Instead, gravity will choreograph a slow, majestic dance. The galaxies will begin to merge, their shapes stretching and warping as tidal forces fling stars into vast arcs that span hundreds of thousands of light years. Over the course of several billion years, their spiral arms will distort and intertwine, and both galaxies will lose their individual identities. Computer simulations conducted by NASA and other research institutions give us a stunning preview of what will happen. After the first encounter, the galaxies will pass through one another, recoil under gravity, and then fall back together for a second, slower embrace. Over time, their stars will settle into new orbits, forming a single, larger elliptical galaxy. Astronomers already have a name for this future structure: Milkomeda, or sometimes Milkdromeda, a new cosmic giant that will unite the stars of both galaxies into one colossal system. At the heart of this merger, the two supermassive black holes that currently sit at the centers of the Milky Way and Andromeda will also spiral toward each other. Each of these black holes contains millions of times the mass of our Sun. As they draw closer, they'll begin orbiting one another, creating ripples in space-time, known as gravitational waves. Eventually, they'll merge into an even larger black hole, unleashing a burst of gravitational energy that will echo across the cosmos. For our solar system, the consequences of this galactic union are uncertain but fascinating. The vast distances between stars mean that the Sun and its planets will likely pass through the merger unscathed. However, their position within the galaxy will change dramatically. Simulations suggest that the solar system might be flung farther out into the outer regions of Andromeda, carried by gravitational tides as the galactic structures merge and reorganize. To future observers living on a distant Earth, or whatever replaces it, the night sky would be utterly transformed. The familiar patterns of the constellations would vanish, replaced by new ones formed from stars that once belonged to two separate galaxies. The combined galaxy, Andromeda, will be brighter, more massive, and more spherical than either of its predecessors. Many of its stars, particularly those from the densely packed galactic cores, will cluster toward the center, while new waves of star formation may ignite as clouds of interstellar gas collide and compress. In some regions, vast nebula will give birth to fresh generations of stars, while in others, the interstellar medium will be consumed or blown away by stellar winds and supernova explosions. Over billions of more years, Andromeda will slowly age and quiet, its blue stars burning out and leaving behind a galaxy rich in ancient red suns, a mature, majestic remnant of two once spiral galaxies. In the far, far future, perhaps tens or hundreds of billions of years from now, Andromeda itself may drift in isolation. The expansion of the universe, driven by dark energy, is accelerating, meaning that distant galaxies are receding from us faster and faster. Eventually, only Andromeda and its closest satellites, remnants of the local group, will remain gravitationally bound together. Everything else, all other galaxies, will fade beyond the horizon of visibility, their light stretched into invisibility by the expansion of space. Our cosmic neighborhood will become an island universe, adrift in an ever-darkening sea. This coming merger between the Milky Way and Andromeda reveals something profound about the nature of cosmic time. When we talk about billions of years, it's easy to think of such numbers as abstract, but in reality, these processes are happening right now, just at a pace too slow for human senses to perceive. The gravitational pull between the galaxies is constant, their motion relentless. Every second brings them infinitesimally closer. The universe, vast and patient, is already setting the stage for one of the most magnificent events in its long history.
And here lies the grand irony. Humanity dreams of reaching Andromeda, of crossing the vast gulf of space that separates us, but in the universe's own slow rhythm, Andromeda is already coming to meet us. The cosmic distance we find so daunting today will, in the fullness of time, shrink to nothing. The two galaxies will blend their stars, their worlds, their destinies. In a way, we are already connected, gravitationally bound, drawn together by a silent force that will one day make us one. If any form of life survives on Earth or among the stars in 4 billion years, those beings will not look out and see Andromeda as a distant spiral across space. They will live within a galaxy forged from its union, part of a new, larger whole, born from the gentle collision of two ancient star cities. The question of how long it would take to reach Andromeda will have become meaningless, because by then, Andromeda will no longer be there, it will be here. We and Andromeda will share a single galactic heart. And perhaps in that far future, when new civilizations gaze into the sky of Andromeda, they will wonder about the same questions we ask now: how vast the universe is, what lies beyond, and whether there are other galaxies slowly making their way toward them too. The cycle of curiosity, awe, and exploration will continue, written into the same laws of gravity and motion that bind our two galaxies together. When we pause to take in the sheer scale of what we've been talking about,
distances measured not in miles or kilometers, but in millions of light years, something quietly transformative happens. Our minds stretch to grasp the enormity, and in that effort, we start to see ourselves differently. The question of how long it would take to reach the Andromeda Galaxy becomes more than a matter of numbers or propulsion systems. It becomes a reflection on the limits of human imagination and on our small yet extraordinary place in the grand architecture of the cosmos. To understand how vast Andromeda truly is and how impossibly far away is to experience a kind of cosmic humility. The light we see from it tonight left that galaxy around the time when early humans were first learning to make simple tools on Earth. Every photon that reaches our eyes has been traveling across the void for more than 2 million years, undisturbed, untouched, a silent messenger from another island of stars. And yet, despite that inconceivable distance, we can see it with the naked eye on a clear night, a faint smudge in the constellation Andromeda. That alone is astonishing. When you look at it, you are literally seeing across time, witnessing ancient light that began its journey long before our species even existed. Moments like that remind us just how young and small we are in the grand timeline of the universe. Our entire history, every civilization, every discovery, every dream occupies just the tiniest fraction of cosmic time. The universe is 13.8 billion years old, and the Milky Way and Andromeda have been evolving for nearly that entire span. The Earth itself is about 4.5 billion years old, and humanity, in its modern form, has existed for only about 300,000 years. If we represented the age of the universe as a single year, all of human history would fit into the final few seconds before midnight on December 31st. And yet, in those few seconds, we have begun to ask questions bold enough to reach across galaxies. That, perhaps, is the most remarkable part of the story. Not how far away Andromeda is, but that a small, fragile species on a tiny blue world has managed to comprehend that distance at all. We are creatures who evolved to hunt, to build fires, to survive, and yet we've also built telescopes that can peer into the edge of the observable universe. We have developed mathematics and physics capable of describing the birth of stars, the curvature of space, and the acceleration of cosmic expansion. From a cosmic perspective, we are infinitesimal, smaller than a speck of dust in a single galaxy among trillions, and yet we are the part of the universe that can understand itself. That is no small thing. When we contemplate distances like 2.5 million light-years, the mind almost rebels. Numbers that large dissolve our normal sense of scale. We can't truly feel them. A single light-year, the distance light travels in 1 year, is nearly 10 trillion kilometers. Multiply that by millions, and the result becomes beyond comprehension. The space between the Milky Way and Andromeda is not an empty corridor, but a vast, diffuse ocean of darkness, thinly scattered with hydrogen atoms, stray stars, and invisible dark matter. Crossing it, even in thought, forces us to confront both our insignificance and our persistence. And yet there's something beautiful about that. To feel small in the face of the cosmos is not a defeat, it's a recognition of belonging. The same laws that guide Andromeda's stars and shape the galaxies also govern us. The carbon in our bodies was forged in ancient stars that exploded long before the sun existed. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was born in the heart of some long-dead star. In a very literal sense, we are the universe made conscious. When we gaze at Andromeda, we are looking at distant kin. There's another humbling truth here. Even if humanity never sets foot beyond the Milky Way, the act of imagining the journey, of daring to wonder, is a kind of exploration in itself. We may never build a ship that can traverse the Gulf to Andromeda, but our minds have already made the trip countless times. We've mapped it, simulated it, and dreamt of what it would be like to arrive. That's what sets us apart, our curiosity, the ability to look at something unimaginably distant and still say, what if? In a universe that operates on timescales of billions of years, our lives are brief flickers of awareness. But in those flickers, we ask immense questions. Where did we come from? Where are we going? Are we alone? These are the questions that define us as a species. They're the same questions that drive us to build telescopes, to launch probes, and to study galaxies like Andromeda in the first place. Even though we might never reach it, Andromeda calls to us as a symbol of possibility, a reminder that there is always something more to seek, something just beyond our reach. And perhaps that is what makes this entire topic so profoundly human. We live on one tiny planet orbiting an ordinary star, in a galaxy that's just one among trillions, and yet we care enough to measure the distance to another galaxy, to calculate how long it would take to get there, and to dream about crossing the unimaginable distance. That's not arrogance, that's aspiration. The same impulse that drove our ancestors to cross oceans and explore continents now drives us to look beyond the stars. Our species may be small, but our curiosity is vast enough to fill the universe. It's worth remembering that every discovery in astronomy, every revelation about our place in the cosmos, has begun with that same combination of wonder and humility. The first humans to notice the Milky Way stretching across the night sky probably couldn't imagine that it was an entire galaxy filled with billions of stars. Centuries later, when telescopes revealed that Andromeda was another galaxy altogether, it shattered our understanding of the universe, expanding it from one island of stars to an ocean of galaxies. Today we know there are likely 2 trillion galaxies in the observable universe, and perhaps countless more beyond that. To exist in such a reality and be aware of it is nothing short of miraculous. So when we look toward Andromeda and think about how long it would take to reach it, we're not just performing an exercise in physics, we're participating in a timeless act of wonder. We're acknowledging both our limitations and our potential. We're recognizing that even though we are small, we are capable of conceiving something infinitely larger than ourselves, and that might be the most extraordinary ability the universe has ever produced.
In the end, reflecting on these vast distances doesn't diminish humanity. It elevates us. To know that we are tiny in the grand scheme of things is to understand just how precious consciousness is. We are the eyes of the cosmos, the voice of the stars, the brief but brilliant flicker of awareness that asks the universe what it is. And even if we never touch Andromeda, the very act of wondering about it ensures that part of us, the part that dreams, has already crossed the void. Looking back over everything we've explored, the question that started this journey, how long would it take humanity to reach the Andromeda Galaxy, has led us far beyond simple numbers. It has carried us through the structure of the cosmos itself, from the immense distance separating our galaxy and its nearest neighbor to the limits of human engineering, the boundaries set by the laws of physics, and the sheer wonder of contemplating something so far beyond our reach. What began as a question of travel time has become a meditation on what it means to be a small, curious species staring out into an infinite universe. At the heart of it all lies the staggering distance, 2.5 million light-years. That figure alone encapsulates the scale of our cosmic environment. Light, the fastest thing in existence, traveling at about 300,000 kilometers per second, still takes millions of years to cross that gulf. In human terms, that's nearly 24 quintillion kilometers, a number so immense it almost defies meaning. It's not just far, it's a separation that dwarfs even our wildest imaginings of space travel. The nearest star system, Alpha Centauri, is only 4.37 light-years away, a mere fraction of that distance. And even reaching it with today's fastest spacecraft would take tens of thousands of years. Andromeda, by contrast, is 500,000 times farther. That's where the limitations of our current technology become painfully clear. The fastest spacecraft ever built, the Parker Solar Probe, the Voyager probes, and New Horizons, travel at extraordinary speeds by human standards, hundreds of thousands of kilometers per hour. Yet even at those velocities, a journey to Andromeda would take billions or tens of billions of years. That's longer than the universe itself has existed. And even if those spacecraft could somehow maintain their top speed indefinitely with perfect precision and no degradation, they would still arrive long after every star in the Milky Way had burned out. In practical terms, reaching another galaxy with today's propulsion systems is not merely difficult, but impossible. When we acknowledge that, we turned our attention to the future, to the realm of theory and imagination, where scientists and dreamers alike envision engines that could someday carry us beyond the stars. Concepts like nuclear fusion drives, antimatter propulsion, and light sails hint at a future where travel between stars and perhaps even galaxies might become marginally feasible. These technologies could, in theory, propel a craft to significant fractions of light speed. Even then, however, the journey to Andromeda would still take millions of years, not billions. An enormous improvement, but still far beyond any human lifetime or civilization's endurance. Such missions might one day be achieved by robotic probes, capable of operating indefinitely, but for living travelers, the gulf remains unbridgeable. And then, of course, there is the speed of light limit, one of the fundamental laws of our universe. Einstein's theory of relativity tells us that as an object with mass accelerates toward light speed, its energy requirements grow toward infinity. It would take infinite energy to reach light speed, a physical impossibility. That rule defines a hard boundary for all conventional propulsion ideas. It's the reason why even our most advanced hypothetical spacecraft, no matter how exotic their engines, will always fall short of traveling at the ultimate cosmic velocity. However, if we could somehow travel at a significant fraction of light speed, say 10%, 50%, or 90%, the picture changes dramatically. At 10% of light speed, a journey to Andromeda would take about 25 million years. At 50%, around 5 million years, and at 90%, just 2.7 million years. Those numbers are still immense, but they move us from the realm of impossibility into that of deep theoretical plausibility. Yet even then, for the travelers aboard such a ship, time dilation would make things even stranger. The faster they move, the slower time passes for them. At near light speeds, a crew might experience only a few years or centuries of travel time, while millions of years pass in the universe outside. They could, in theory, reach Andromeda within their own lifetimes, but they would arrive in a universe unimaginably older than the one they left. Of course, that's assuming we could ever build a ship capable of sustaining life under those extreme conditions, a monumental engineering and biological challenge. That's why robotic probes appear to be the more likely candidates for intergalactic travel. Unlike humans, machines do not age, hunger, or sleep. They can wait out the eons, cross the emptiness between galaxies, and awaken on the other side to record and transmit their findings. In fact, our first ambassadors to other galaxies may already exist in the form of the Voyager and Pioneer spacecraft, which will drift endlessly through interstellar and intergalactic space long after our species is gone.
We also explored ideas that exist only on the edges of science: wormholes, warp drives, and space-time manipulation. These concepts offer tantalizing shortcuts that might, theoretically, allow for near instantaneous travel between distant points in space. But they remain speculative, bound more to the realm of mathematics and imagination than to practical physics. To make them real would require understanding and manipulating forms of energy that we don't even know how to detect yet. Still, these ideas persist because they represent the ultimate expression of human curiosity. A refusal to accept that any distance, no matter how vast, is truly insurmountable. And just when the gulf between galaxies seems most daunting, the universe reminds us of its grand cycles, because Andromeda and the Milky Way are already moving toward one another. In about 4 billion years, they will merge to form a single massive galaxy, Andromeda. When that happens, the boundary between us and them will vanish entirely. Every star in both galaxies will share a common home, orbiting a new center of gravity. In a cosmic sense, Andromeda will one day come to us. The long journey we've been imagining will unfold not by the hands of human engineers, but through the quiet, relentless pull of gravity. When we reflect on all of this, the enormous distances, the limitations of our technology, the speed of light, and the future merger of galaxies, what emerges is a profound sense of scale and humility. The universe is vast beyond comprehension, and yet here we are, able to measure, model, and dream about it. The numbers might remind us of how small we are, but they also reveal something extraordinary: our ability to think beyond those limits. That's what truly matters. Intergalactic travel, for now, remains a dream, a vision confined to imagination, mathematics, and science fiction. But in asking the question of how long it would take to reach Andromeda, we've done something deeply human. We've dared to confront the immensity of existence and to ask, what if? And that question, that spark of curiosity, is the first step of every great journey humanity has ever taken. Even after all the vast numbers, the limits, and the impossible distances, one truth rises above everything else. Humanity's capacity for wonder is as infinite as the cosmos itself. While the Andromeda Galaxy may remain far beyond our physical reach for now, the very act of imagining the journey has already taken us somewhere extraordinary. It has drawn us out of the confines of our small world and placed us in a story billions of years wide, a story written in light, motion, and time. And in that story, we are not passive observers, we are participants, thinkers, and dreamers who refuse to stop asking what lies beyond. Throughout history, every generation has looked up at the night sky and felt that same pull, that quiet invitation to explore. When ancient people first traced patterns in the stars, they were unknowingly taking the first steps toward astronomy. When Galileo turned his telescope to the heavens, he shattered humanity's sense of isolation, revealing that Earth was not the center of the universe, but just one planet orbiting an ordinary star. When we sent the Voyager probes into space, we took that next symbolic leap, sending our presence, our voice into the cosmos. And each of these moments began the same way, with curiosity, with someone daring to look a little farther than before.
Andromeda may be 2.5 million light-years away, but distance has never been what defines us. What defines us is the will to reach, the desire to understand, and the refusal to accept that there are limits to knowledge. The same spirit that built the pyramids, sailed across oceans, split the atom, and landed humans on the moon is the same spirit that now looks at another galaxy and says, maybe someday. It's that restless curiosity, that spark, that makes us human. Perhaps the Andromeda Galaxy will never host human footsteps. Perhaps no ship we build will ever bridge that gulf. But one day, our descendants, human or otherwise, might find a way. Maybe they will harness energies we can't yet imagine, fold space itself, or travel as consciousness encoded in light. Maybe, long after we are gone, the machines we send out will arrive and announce, in their own way, that humanity once lived, once dreamed, and once reached for the stars. In that sense, the voyage will never truly end. It will continue as long as there are minds willing to wonder. And there's another truth hidden in this dream of intergalactic travel. Even if we never leave our galaxy, we are already part of something unimaginably vast. The atoms in our bodies were born in ancient stars, scattered by supernovae, gathered again into new suns and worlds. We are the universe looking back on itself, stardust with awareness. When we gaze at Andromeda shimmering faintly in the night sky, we're not looking at something separate from us. We are looking at our own cosmic reflection, at a galaxy bound to us by gravity and destiny. One day, long after our species is gone, the Milky Way and Andromeda will merge and our stars will mingle. In the grand timeline of the cosmos, we are already on our way there. So, the next time you step outside on a clear night and see that faint patch of light, that ancient whisper from across the void, remember what it represents. It is not just a galaxy. It is a promise. A reminder that no matter how far the distance or how impossible the journey, humanity will always keep looking outward. Because within us is a spark that no distance can extinguish. A drive to explore, to understand, and to belong to something greater. We are wanderers in both body and spirit. We may not yet have the ships or the power to reach another galaxy, but our imagination travels faster than light, carrying us across the universe in thought, in art, in science, in hope. One day, perhaps millions of years from now, something or someone born of humanity may finally touch Andromeda's stars. And when that day comes, it will not just be a triumph of technology, but a testament to a single unbreakable truth, that the universe has given rise to a species that dares to dream of touching the infinite. Until then, we will continue to look upward, not in despair at the distances, but in awe at the possibilities. For every question we ask of the cosmos brings us one step closer to understanding not just the universe, but ourselves. And perhaps that is the greatest journey of all, the voyage of awareness, of curiosity, of wonder. So while Andromeda may be beyond our reach for now, it will never be beyond our imagination. And as long as we keep imagining, as long as we keep looking to the stars, there will always be new frontiers waiting to be discovered. The cosmos is vast, but so is the human spirit. And that spirit, more than any engine or technology, will be the force that one day carries us among the galaxies. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.